Lesson 5. Electronic Speed Controller, ESC. The ESC, Electronic Speed Controller, is an electronic component in the form of a printed circuit board that controls the rotation speed of the motors in an FPV drone, their direction of rotation and braking. It receives commands from the flight controller and converts them into electrical signals that control the operation of the motors. Additionally, the ESC converts direct current, DC, to alternating current, AC. Accordingly, it serves as a bridge between the motor and the battery, regulating the voltage that the motor receives from the battery. Electronic speed controllers are a critical component in FPV drones as they directly affect flight performance and reliability. The ability of the drone to perform complex maneuvers, the stability of its flight, and the efficiency of energy consumption depend on the correct selection and configuration of the ESC. The flight controller is the brain of the FPV drone, which collects data from various sensors, accelerometer, gyroscope, barometer, etc., and receives commands through the receiver, RX, from the remote control. Based on this data, the flight controller generates control signals for the ESC. The main function of the ESC is to control the rotation speed of the motors. The flight controller generates control signals that correspond to the pilot's commands, altitude, speed, direction, etc. These signals are transmitted to the ESC through special cables. The ESC receives these signals and converts them into corresponding commands for the motors. This usually involves changing the voltage supplied to the motors. Based on these commands, the ESC adjusts the rotation speed of the motors, which affects the speed, altitude, and direction of the drone's flight. The ESC also allows for changing the direction of rotation of the motors. The brushless motors used in FPV drones have 3 phases of stator windings. The ESC controls the supply of electrical pulses to these windings in a specific sequence to create a rotating magnetic field, which causes the rotor of the motor to spin. The direction of motor rotation can be changed in 2 ways. Through ESC software. Modern ESCs have firmware that allows changing the direction of motor rotation through software settings. For example, the BL-Heli-32 firmware allows you to change the rotation direction using a software interface. Or through physical reconnection of wires. If necessary, you can change the direction of the motor by reconnecting 2 of the 3 wires that connect the ESC to the motor. However, this method is less convenient and is used less frequently. Active braking is one of the important functions that allows electronic speed controllers, ESC, to provide precise and rapid deceleration or complete stopping of the motors. This is especially useful for performing complex maneuvers and quickly responding to commands from the flight controller. Active braking works by creating back electromotive force, EMF, that opposes the rotational motion of the motor's rotor. This is achieved by controlling the supply of electric current to the stator windings of the motor. In traditional brushless motors, when the current is cut off, the motor gradually slows down due to internal friction and air resistance. Active braking accelerates this process. Advantages of active braking. Active braking allows the drone to quickly change direction or come to a stop, which is important for performing complex maneuvers, especially in racing drones and during freestyle flying. Instead of gradual deceleration, active braking enables instantaneous reduction of motor speed, providing quick responsiveness to the pilot's commands. With more precise control over motor speed, active braking contributes to better stability and predictability of the drone's behavior in the air. Modern ESCs come with built-in protective features such as overload protection, overheat protection, and low-voltage protection. This helps prevent damage to the motors and the ESC itself in case of unforeseen situations. The ESC optimizes energy consumption, ensuring efficient operation of the motors. This allows for reduced battery usage and extends the flight time of the drone. Different firmware such as BL-Heli-S, BL-Heli-32, Bluejay, M32 provide additional features and capabilities for configuring the ESC. They can enhance the performance and efficiency of the drone as well as provide support for various signal transmission protocols. In FPV drone control systems, Various protocols are used to transmit commands from the flight controller, FC, to the electronic speed controller, ESC. These protocols determine how signals are transmitted and how quickly and accurately these signals are processed by the ESC. Let's take a closer look at each of the protocols: PWM, PPM, Oneshot, Multishot, and DShot. PWM, pulse width modulation, is the oldest and most common protocol for transmitting signals from the FC to the ESC. It uses changes in pulse width to convey information about the motor's rotation speed. How it works: the PWM signal transmits information about the motor's speed by varying the width of the pulses. The time interval during which the pulse is in the high state, on, determines the command for the ESC. Signal frequency: the standard frequency of the PWM signal for ESCs is typically 50 Hz, 20 milliseconds period. This means that the signal is updated 50 times per second. Advantages: simplicity of implementation and compatibility with most hardware. Disadvantages: relatively low update frequency, which can lead to delays in control, making it unsuitable for high-speed maneuvers in FPV drones. PPM, pulse position modulation, is a protocol that is typically used for transmitting signals from the receiver to the FC, but it can also be used for sending commands to the ESC. How it works: information is transmitted by changing the position of pulses in a series. One PPM signal can contain multiple channels, usually up to 8. Advantages: the ability to transmit multiple channels over a single wire, reducing the number of required connections. Disadvantages: relatively low update frequency and delays in signal transmission. Oneshot is a protocol specifically designed for FPV drones to provide faster and more accurate transmission of commands from the FC to the ESC. Oneshot 125. Signal updates occur much faster than with PWM, with a frequency of up to 8 kHz. Signals are transmitted using pulses that are 8 times shorter than PWM pulses. Oneshot 42, an even faster variant of Oneshot, which has a frequency of up to 24 kHz, providing even lower latency in command transmission. Advantages: high update frequency and lower latency, which improves the drone's responsiveness and stability. Disadvantages: requires compatible hardware and is less versatile compared to PWM. Multishot is an even faster protocol than Oneshot, designed to provide ultra-fast signal transmission. How it works: signals are transmitted at a frequency of up to 32 kHz, ensuring an extremely quick response of the ESC to commands from the FC. Advantages: the highest update frequency among analog protocols, providing the fastest and most accurate response of the motors. Disadvantages: high hardware requirements and the need for compatible FCs and ESCs. DShot, digital shot, is a digital protocol that provides command transmission directly in the form of digital signals. How it works: information is transmitted in the form of digital packets, eliminating errors and inaccuracies that can occur in analog protocols. There are different versions of DShot, such as DShot 150, DShot 300, DShot 600, and DShot 1200, where the number indicates the speed in kilobits per second, kbps. Advantages: high accuracy, no need for calibration, as with PWM, and the ability to transmit additional data. Disadvantages: requires modern hardware and compatible FCs and ESCs. Thus, each of the control protocols has its advantages and disadvantages, and the choice depends on the specific needs and capabilities of your FPV drone. PWM remains the most common due to its simplicity and compatibility, but for high-speed and precise maneuvers, the faster and more modern protocol, DShot, is recommended. The compatibility of hardware among all electronic components of your FPV drone is crucial. The ESC must be compatible with your flight controller. Some ESC firmware may only support certain types of FC microcontrollers. For example, only G4, F4, and F7 support ESCs with AM32 firmware. Make sure that your flight controller supports the ESC protocol used for communication between the FC and the ESC. For instance, if the ESC firmware uses the DShot protocol, your flight controller must also support it. Each 4-in-1 ESC has its own mounting order on the frame. It is marked with the numbers 4, 2, 3, and 1, where 4 and 2 are at the front of the drone and 3 and 1 are at the rear. The number 4 always corresponds to the front left motor in a classic X-frame assembly, and it can be used as a reference for determining the direction of motor rotation for the drone. If 4 and 2 are not positioned at the front of the drone will receive incorrect commands to the motors during control, making it impossible to operate. In extreme cases, this can be corrected by changing the code in the FC software. FPV drones have a diagonal motor rotation direction where each diagonal operates opposite to the other. One pair of motors will always rotate clockwise, while the other will rotate counterclockwise. This is done for the following reason: balancing thrust. When a motor spins, it creates thrust in the opposite direction, according to Newton's third law. If all motors rotated in the same direction, the drone would begin to rotate around its axis. However, when the motors rotate in different directions, the thrust from one motor compensates for the thrust from the other, helping the drone remain stable. Configuring the motors in this way allows the drone to maneuver easily and perform complex flight maneuvers. In FPV, there are two motor rotation configuration schemes: props in and props out. Props in. In this configuration, one pair of motors, the front left and rear right, will rotate clockwise, CW, while the other pair, the front right and rear left, will rotate counterclockwise, CCW. Advantages. The props in configuration will exclusively allow the turtle mode for drones with ducks. This is because this motor rotation scheme provides the necessary airflow to lift the drone off the ground when it is inverted. During takeoff from the ground or sand, dirt will not enter the frame and affect the electronic components. The presence of dust on electronic components can lead to short circuits. However, the advantages end here. Disadvantages. During flight, anything that gets caught in the front propellers will also enter the drone's camera view. This can potentially dirty your camera, making it impossible to see, disorienting you, and causing your drone to crash. In the event of a collision with a tree, branches, or any other obstacle, the propellers will tend to suck in the obstruction. This will cause more damage to your drone, the motors, and the propellers themselves. Props out. In this configuration, one pair of motors, the front left and rear right, will rotate counterclockwise, CCW, while the other pair, the front right and rear left, will rotate clockwise, CW. Advantages. Any dirt that you encounter while the drone is in motion will be pushed away by the propellers in the opposite direction from the camera. This way, your camera will remain clean, and you will be able to control the drone without issues. In the event of a collision with a tree, branches, or any other obstacle, the propellers will help push the drone away from the obstruction, potentially reducing damage to the drone. Disadvantages. If you choose to launch your drone from the ground, dust will be pushed into the frame by the airflow, potentially leading to short circuits and burning out the FC or ESC. Currently, the market is flooded with various types of ESCs. There are ESCs in AIO configurations, 4-in-1 ESCs, 6-in-1 ESCs for hexacopters, 8-in-1 ESCs for Cinelifter FPV, and individual ESCs for each motor. However, the 4-in-1 ESCs dominate the market. This means that one printed circuit board integrates 4 separate ESCs, each controlling a separate motor. Accordingly, we can connect 4 motors to one ESC printed circuit board. 4-in-1 ESCs provide better weight distribution due to their centralized mass within the FPV drone frame, which improves the drone's responsiveness. However, if one of the ESC microcontrollers on such a printed circuit board fails, the entire 4-in-1 ESC board will need to be replaced. If you miscalculated the required power of the ESC for your motors, or if you flew at 90% throttle for the entire flight, the ESC may overheat and its microcontrollers could burn out. Let's talk about individual ESCs for each motor. Accordingly, a separate ESC controls only one motor. The advantage of individual ESCs is their ease of use and cost-effectiveness when it comes to replacing a damaged ESC. You will only need to replace the damaged one, rather than all the ESC boards. Another advantage is that individual ESCs receive more airflow and have better cooling capabilities, as they are typically mounted on the arms of the FPV drone. However, all these advantages are offset by a greater and more serious number of disadvantages. Firstly, installing individual ESCs requires more soldering and the use of more wires. Since the ESCs are located further from the center of the drone, this increases the drone's moment of inertia and potentially reduces its responsiveness. The longer the wire length and the greater the distance from the flight controller, the more delay there will be in the transmission of control signals from the FC to the ESC. To improve the operational potential of each ESC, it becomes necessary to connect a separate capacitor to each of them. Additionally, we cannot solder each individual ESC directly to the flight controller and power each one from the battery. They simply cannot withstand the voltage supplied by the battery. Therefore, we need an additional printed circuit board, PDB, that will combine all the ESCs, receive the direct current from the battery, and distribute the necessary voltage to each ESC. The flight controller will first send motor control signals to the PDB, which will then transmit the signals to each ESC. All these disadvantages, in the form of increased wiring, additional capacitors, and the extra PDB, lead to an increase in the overall weight of the FPV drone and its inertia. The advantage of cost-effectiveness of individual ESCs becomes questionable because 4-in-1 ESCs are already quite reliable and rarely require replacement. It is essential to choose an ESC that can operate with the voltage supplied by your battery. For example, if you are using a 4S battery with a charged voltage of 16.8 volt, your ESC must be capable of handling that voltage. Using a battery voltage that is too high for your ESC can lead to its damage. Most ESCs today support input voltages from LiPo batteries of 4-6S, while some only support up to 4S or even lower. To correctly choose an ESC for your drone that can handle the current consumption of your motor, you need to understand the current consumption of the motor itself. Knowing the number of amps consumed by the motor according to its specifications, you should select an ESC with a nominal current rating that is 10 ampere higher. For example, if the motor consumes 20 ampere, the ESC should be capable of handling 30 ampere and supplying it to each motor. Alternatively, if all 4 motors consume a total of 100 ampere, the ESC should be able to handle and supply 140 ampere simultaneously to all motors. Why is this 10 ampere buffer necessary? It is to protect the ESC from overload and overheating due to sudden throttle spikes. In the manufacturer's description of any ESC, you will see specifications for the nominal current that the ESC can handle and the peak current. Nominal current. This is the current at which the ESC can operate for an extended period without overheating. It is also referred to as continuous current. However, when the FPV drone needs to perform sharp, intense maneuvers, the ESC can supply peak current to provide additional power. This is the maximum current that the ESC can handle and deliver, but only for a short duration, typically no more than 10 seconds. In the description, it is referred to as max or burst current. There is no point in buying an ESC with an excessively high current rating, as it will be much more expensive and will only increase the weight of the drone. If you purchase an ESC with a lower current rating than what the motors consume, that ESC will burn out from overload. The connections between the flight controller and the ESC use ground, VCC 5 volts, tele, pin for connecting motor telemetry, cur, signal pin for distributing voltage to each motor, and a certain number of signal pins, S, for each motor to transmit control signals. If the flight controller has only 4 signal pins for motors, it means that no more motors can be connected to it. Thus, if the ESC is 8-in-1, it will necessarily have the following pins for connection to the flight controller: ground, VCC 5 volts, S1, S8, signal pins for each motor, tele, pin for connecting motor telemetry, and cur, signal pin for distributing voltage to each motor. The ESC is usually located beneath the flight controller and connected via wires. Therefore, the ESC should generally have the same actual and mounting size as the flight controller board, allowing for easy integration between the two. The most popular type of 4-in-1 ESC is available in the following mounting sizes: 30.5 mm by 30.5 mm, 25.5 mm by 25.5 mm, and 20 mm by 20 mm. It is important to choose an ESC mounting size that matches the mounting size of your flight controller and frame. Generally, the larger the ESC in size, the more durable and powerful it is due to larger transistors. Additionally, it is important that the actual size of the printed circuit board is not larger than the width of the FPV drone frame. Otherwise, dirt will constantly get onto the board, increasing the likelihood of short-circuiting the electronic components. Furthermore, you will frequently bump into the motor power wires with your hands, potentially causing them to break. Firmware is the operating system installed on the main microprocessor of the ESC. It receives and processes all signals coming from the flight controller and then, using its internal instructions, controls the transistors, MOSFETs, to regulate the amount of current supplied to each motor. If the current exceeds a safe level, the firmware sends signals to reduce the power of that current. The ESC consists of microcontroller unit, MCU, gate drivers, MOSFETs, transistors, voltage regulator, LDO, current sensor, filtering capacitors. The interaction of all elements of the ESC occurs through commands received from the firmware. It is like an orchestra, with the firmware acting as the conductor. Microcontroller unit, MCU, this is the brain of the ESC. The ESC firmware is loaded into it, and all processes of information processing and transmission of control commands to other ESC elements are executed here. Gate drivers. The firmware controls the gate drivers, indicating when to open and close the MOSFETs, transistors. MOSFETs. These are a type of transistor that regulates the amount of electrical current supplied to the motor. The firmware controls the transistors through the gate drivers. Voltage regulator, LDO, this provides stable voltage for the MCU and other ESC components. The firmware can monitor the voltage through the LDO and adjust it as needed. Current sensors, these monitor the current flowing through the ESC. This information is used by the firmware to protect the ESC from overload. Filtering capacitors, these store electrical charge and release it when needed to smooth out voltage fluctuations. Although the firmware does not directly control the capacitors, it uses data from the current sensors to determine when the capacitors should release charge to smooth out voltage fluctuations and subsequently records this information. Thus, based on this data, we can better calibrate our ESC to increase its efficiency. Currently, there are 4 main firmware types used for ESCs: BL-Heli-S, Bluejay, BL-Heli-32, and AM-32. There are also older firmware types such as KISS, BL-Heli, and SIMON-K, but these are outdated and do not meet the needs of modern FPV drones, so there is no point in discussing them. BL-Heli-S firmware is the second generation of the BL-Heli firmware, specifically developed for ESCs with faster 8-bit busy beam processors. This firmware is open source, but it does not support the bidirectional digital protocol DShot. For example, through beta flight, there is the possibility to configure RPM filters to eliminate vibrations caused by the motors and propellers, which affect the performance of the gyroscope on your flight controller. Why is it impossible to configure this without DShot? Because the bidirectionality of this protocol allows for the transmission of data from the ESC regarding the motor's rotation speed to the flight controller. Additionally, without DShot, you will not be able to see the telemetry of your ESC's performance. Although the official BL-Heli-S firmware is no longer updated, as development has shifted to the newer BL-Heli-32, a special firmware has emerged that supports the hardware used with BL-Heli-S, offering advanced features and performance comparable to the latest and more expensive BL-Heli-32 ESCs. A prominent example is Bluejay. Many users upgrade from BL-Heli-S to Bluejay for optimal performance. The advantages of Bluejay include its support for the bidirectional DShot protocol. Accordingly, you will have the opportunity to better tune the flight characteristics of your drone. It has fixed PWM, pulse width modulation, frequency settings, 24 kHz, 48 kHz, and 96 kHz, to enhance motor responsiveness and efficiency, potentially increasing flight time by up to 30%. Higher PWM frequencies can improve motor efficiency but may reduce the braking force of the motor. Bluejay supports ESC telemetry and has additional parameters that can be adjusted for greater personalization of your drone, such as melodies during drone startup, frame lighting, etc. BL Heli 32, AM32. BL Heli 32 is the third and latest generation of the BL Heli firmware for ESCs. It is specifically designed for 32-bit processors. However, this firmware has a closed source code, meaning that the firmware code is not available for public access for modification or improvement. Despite the fact that BL Heli 32 offers certain advantages and unique features over the older BL Heli S, it is significantly more expensive and does not provide a substantial improvement in flight performance. Therefore, many pilots still prefer to purchase the cheaper BL Heli S ESCs and reflash them to Bluejay. The difference between Bluejay and BL Heli 32 is minimal, with the main distinction being that this firmware is installed on a 32-bit processor. This automatically provides a boost in the processing speed of all information processes and motor control processes. As of June 2024, the manufacturers of BL Heli 32 have discontinued production and revoked all licenses for this firmware from ESC printed circuit board manufacturers. Consequently, this firmware, like BL Heli S, is no longer updated. Therefore, if you are completely satisfied with the capabilities of the latest version of BL Heli 32, you can continue to use it. However, if it does not meet your needs and you require constant improvements to your drone's capabilities, you have the option to reflash BL Heli 32 to the newer AM32 firmware. AM32 is an open-source firmware for ESCs developed with modern ARM-based ESCs in mind. What is great about AM32 is that it does not just try to match BL Heli 32. In several aspects, it surpasses it, such as in operational efficiency. This makes AM32 a viable and attractive alternative to BL Heli 32 without the need to pay for licensing. Therefore, ESCs equipped with AM32 can be more cost-effective. What AM32 offers? Open-source firmware. Software that can be updated via Betaflight pass-through, supports only G4, F4, and F7 generation flight controllers. Support for servo PWM, DShot 300, and DShot 600 protocols. Bidirectional DShot. Standard KISS ESC telemetry. Adjustable PWM frequency. Sinusoidal startup mode designed to accelerate larger motors. Motor stall protection. And since AM32 will be updated in the future, it will be more appealing to experienced FPV drone pilots than the outdated version BL Heli 32. Therefore, you can either purchase an ESC with the necessary firmware right away or reflash your current firmware version to another, from BL Heli S to Bluejay, from BL Heli 32 to AM32. What you must know before changing the firmware on your ESC. When reflashing your ESC from firmware that is no longer updated, such as BL Heli S or BL Heli 32, you will not be able to revert to those firmware versions. In other words, the reflashing process is one way. 32-bit ESCs use STM32 processors, similar to those found in flight controllers. Common processors used in ESCs include F0, F3, and F4. Thus, after examining the motor rotation direction schemes in more detail, we can conclude that for drones where we do not need to use the turtle mode, it is better to configure the props out scheme. It has significantly greater and more serious advantages compared to the props in scheme. Its disadvantage can be easily mitigated by launching the drone from a takeoff platform. We can change the direction of motor rotation either through the firmware of the flight controller or by physically reconnecting two of the three wires that connect the ESC to the motor. However, the latter option is used less frequently.